Our group members are Brian Ian Lee, Kui Yishuan, Noor Fadlan Hanis, and lastly Mohammed Hakim. In this case study, a landslide event known as the 2008 Bukit Antarabangsa landslide happened on December 6, 2008 in Ulu Klang, Selangor, Malaysia. The landslide tragedy at Taman Bukit Miwa and Taman Bukit Utama occurred at approximately 3:50 a.m., resulting in the collapse of 14 bungalow houses, 15 injuries, and 4 fatalities. Our site location is at Jalan Wangsa 9, Jalan Bukit Antarabangsa, Jalan Bukit Miwa 2, Taman Bukit Miwa, Ampang, Selangor. The objectives of this study are to analyze the geotechnical factors contributing to the soil failure, to propose suitable site investigation (CI) methods for the landslide area, to implement advanced, integrated site investigation technologies that enhance the accuracy and comprehensiveness of data collection. The main cause of this landslide are soil creep, damaged active pipes, and prolonged rainfall. The information regarding landslide, rainfall data. The monthly rainfall was 594 and 592 mm, respectively, for a total of 1,186 mm. This is equal to 45% of the average annual rainfall in Bukit Antarabangsa over the course of the 5-year period of 2003 to 2008. Geology of the landslide area. The residual soils in this region consist of granite that has been left behind from the parent rock mass at different stages of disintegration. Failure identification. Soil settlement occurs due to inadequate foundation design or high stresses on weak or compressible soils like clay or peat. Proper foundation design is crucial to distribute a structure's weight to stable soil or rock layers. Without this, uneven settling and structural instability may occur. Heavy rain poses risks such as floods, landslides, and infrastructure damage due to poor drainage systems. Excessive precipitation can overwhelm drainage infrastructure, causing floods in both urban and rural areas. Interrelationship for all stakeholders involved: government agencies and authorities, engineers and geologists, contractors and construction companies, local communities and residents. Standard penetration test. Consider this as the site, and here is the point: wish to explore the soil properties at a depth of 1 meter. Now make a borehole up to the desired depth. Place the tripod concentrically above the borehole. Take the gate rod and fix the sampler at bottom. Attach the hammer of 63.5 kg and anvil to the gate rod. Make a marking of 75 cm above anvil to have uniform height of fall. Keep a pulley at the top of the tripod and suspend the rope over it. Attach the hammer to one end of your rope using hook. Make 4 markings along the guide rod starting from the ground surface at an interval of 15 cm each. Now drop the hammer through 75 cm height and start penetrating the soil. Did you start counting the blows? The blows required for 15 cm penetration is not considered, as it is a seeding drive. Blows required for second and third 15 cm, that is from 15 to 30 cm, and from 30 cm and from 30 to 45 cm is recorded. And the end value are recorded. Seismic refraction. Refraction starts very similarly to seismic reflection, but with some major differences. For example, this direct waves matter now, and so does this wave at the critical angle. The wave arrives simultaneously, but here the refracted wave is faster. The top layer is normally slower than the one under it. Therefore, eventually the shortest route is no longer the fastest, because the refracted wave can go at a higher speed. This is typical seismic refraction data, where we can see 2 distinct velocities. The first steeper section is due to the direct wave. The second section is where the refracted wave overtakes the direct wave and has a shallower gradient. This is our design and plan layout. The innovation that we do is user-friendly interfaces and mobile apps. Developers have created user-friendly mobile apps for SPT testing and seismic refraction surveys. These apps guide users step by step through the testing process, providing clear instructions and prompts for accurate data collection. Next is voice command integration. Incorporate voice command technology into testing equipment and software interfaces to allow users to control the testing process hands-free. Users can verbally initiate tests, input data, and receive test results, reducing the need for manual interaction with equipment and improving efficiency, especially challenging field conditions. Management of environmental well-being resulting from SPT implementation, soil and vegetation protection, waste management, and water management. Conclusion. The December 6, 2008 landslip at Taman Bukit Miwa, Bukit Anarabangsa, was caused by high pore water pressure. A detailed examination of geological data, rainfall records, and site conditions revealed key insights into the event's causes and effects. The standard penetration test SPT proved invaluable for assessing soil stability and suitability for stabilization, offering advantages in efficiency, speed, and cost-effectiveness. The report underscores the importance of proactive risk assessment, effective mitigation strategies, and ongoing monitoring to safeguard people, property, and the environment from landslip threats.